joining us. And if you want to send through any questions or comments along the way, please feel free.
Okay, look, we started the technology, and we actually started negotiating with the Australian government, who invented what we now call BioGill at a place called ANSTO, which is the Australian Nuclear Science and Technology Organisation. Originally, ANSTO was working on this technology as a growth platform for penicillin and antibiotics. So wastewater wasn't their first thought. However, for us, it's the low-hanging fruit. Pharmaceuticals is a long lead time to market. So we decided to focus first off on wastewater. And we've developed the technology quite considerably since we first took it on. Originally coming out of the laboratories of ANSTO, the technology was just that. It was a technology and it was never a product. And that was a quantum leap for us to try and turn that from what was a good idea and a very good attached growth membrane into a product that we could market worldwide. The thing that I liked most of all when I first saw the technology was its simplicity. We've tried in a previous company that we used to run here, working in the environmental sector, where we've installed a number of projects. We've tried different technologies in the wastewater field. And the thing I like most of all about what we now call BioGill is that it was very simple. We simply had to lift water to the top of the chamber and allow gravity to bring it back down. And also one of the main factors is that it will optimize to suit best of all whatever you're feeding it. So you don't have to grow specific microbes. The dominant bacteria will take over, and it will optimize itself to suit whatever you're feeding into the system. So I like simplicity because they don't tend to break down, and they just get the job done. Just a couple. We've started with what we're now calling the BioGill Tower. This tower is for us, it's quite a revolution. For the market, I'm not so sure how you're going to receive that, but there's been a lot of work go into this. We've invested a lot of time and money in coming up with the tower. Some of the advantages of this one over previous models is that we've removed the stainless steel framing on the inside, and we've replaced that with engineered polymer. So it's nylon reinforced, extremely strong. But we also have, by doing that, we have a lighter system by about 20 kilograms, so around about 60 odd pounds or more lighter. And also there's no chance of corrosion. So even though we were using grade 316 stainless steel before, you can't beat polymer as far as non-corrosion is concerned. We've also improved the distribution system in the top of the tower that we now call Hydroswell. And the Hydroswell system is quite brilliant actually for spreading the water over the membrane quite evenly. So, and there's additional ventilation on the side as well. One other thing you might notice, just looking at that image on the left-hand side, is that from the outside, you can see there's 6 knobs on each of the external walls. You can undo those knobs with hand, just by unscrewing with your hands, takes seconds. You can remove a wall. In fact, you can remove all 4 walls while the system's actually running. And so from a maintenance perspective, or if you're looking for access to the gills to be able to take off some scrapings or samples, it's terrific for access maintenance-wise. There is a 2-foot square access hatch in the top, through the top of the lid, but also all of those side walls are easily removed for any sort of maintenance or inspection. On the right-hand side, you can see the BioGill Ultra. I'll get Akil to go through that in a little bit further detail. But what we're working on here is a continuous flow system. So we can do batch with the tower, and we can do continuous flow with the Ultra. And that will be a compact type of system that we can use as a plug and play in just about any environment.
Okay, we're now going to pass over to Akil Sultan, our Head of Engineering and Technology, to go through the technological side of the presentation. Akil.
Yeah, good afternoon, everybody, and thanks for joining this webinar. It's a certainly exciting time for us to be talking to people on the opposite side of the globe. Okay, so just to run through basic technical specifications. Things like the temperature range and the biological pH, they more likely biologically dependent. So the temperature is the optimum temperature for the biomass, 65 to 100 degree Fahrenheit, and the pH 6.5 to 8.5. And that's, like I said, more related to the biomass. The actual membranes themselves are resilient, a lot more resilient, and can tolerate a lot more wider range. The nutrient quality, the preferred CMP ratio of 10 to 100 to 1. Again, that's related to the biology. If you're doing sewage, you don't need to worry about that. Sewage is a naturally balanced stream. It's going to have the right BOD to nitrogen to phosphorus ratio. If you're doing industrial wastewater or high-strength wastewater, most likely you will need to dose nitrogen and phosphorus, as you all know. Pre-treatment, we want like screening to what we call 3 millimeters or 1/8 of an inch, basically to protect our hydroswell. The hydroswell has got a 3 millimeter channel inside it where we create the vortex, and basically we don't want that to get blocked. The flow rate per module, the actual flow rate is dependent on the application. So the stronger and more difficult the wastewater, the higher the flow rate. We at the moment got two types. We've got a low flow and a high flow. A typical range, 6 to 8 meters cube an hour. We'll cover that in the next slide. Typical dimensions. So the modular units, 45 by 45 by 88, or 1.1 by 1.1 by 2.2. So that's the basic footprint of the modular unit. The media area is 230 square meters or 2,475 square foot. Minimum height, we like when you guys install these, we like to keep at least a minimum of 600 millimeters clearance on the top. We need access to the top hatch to clean the hydroswell feed manifold and to hose down the top gills. Dry weight, when they're dry, it's quite a nice 200 kilograms or 440 pounds, but very easily handled by a forklift or even a four-man lift. As they get wet and get biomass on them, they start getting heavy, and they could go up to 750 kilograms or 1,650 pounds. The inlet is a 2-inch pressure. When I say pressure, maximum to 10 meters head, about 10 psi roughly. And the outlet is gravity drain. So when we say gravity drain, basically it is gravity, and we like minimum to no restrictions on it. So this here is a photo from our previous model. The new one is a similar concept. Probably just doesn't have the two bars on the top, and that's what we call the hydroswell, our own nozzle feed manifold. So we developed this with basically having gone to the market, done the research, and developed our own. And what we wanted something that doesn't block up with biomass. So you've got a little channel here that creates high velocity. And hence, we found that we're able to run it on high biomass, high sugar wastewaters without blockage. So this is the flow rate. You need about half a meter. The typical range, 10 meters cube an hour. 10 meters cube an hour is about 2,641. I have to admit, I have to get my head around the US units, because the rest of the world is in metric, and the only country that doesn't want to convert to the rest of the world is the US. I'm not used to at all in thinking in US units, but I am doing my best. So the typical flow is 10 meters cube an hour, or 2,641 US gallons per hour. I know you guys use gallon per minute, but it is what it is. And the pressure is 10 kPa or 1.45 psi. So it's very low pressure required to actually get the coverage using the hydroswell. Yeah, next page. So again, we are an attached growth system. So our membranes have what we call an air side and a liquid side. I'll cover that a little bit in more details in the next slide. But I guess what the message or what I want you to take out of this is, when you look at an installation and you open and look at the air side, you get this brownish, earthy smelling biomass, and it looks like what you'd see in a conventional aerobic tank with fine air diffusion, only a lot thicker. It's got a nice, present, earthy smell to it. You go across to the liquid side and you open it up and you get this black, putrid not very nice smelling anaerobic biomass. So what we're doing, instead of growing the two different type of bacteria in different tanks, as you would in a conventional wastewater plant, we're doing it on different sides of the membranes. So, and I'll touch here, if you think of a flat sheet, so the flat sheet membrane is looped around and hanged on a top hanger. And as it is looped on the inside, we're creating an air pocket. And on the outside, as those two, what we call gills, come in contact with each other, they form what we call the liquid side. So the water flows through the liquid side, not in contact with the biomass growing on the inside. And if you, hypothetically, let's start from the outside here and traverse or dive deeper into the biofilm. And if you think what I've got here is I've got ORP, oxygen reduction potential. And what I want to get across is the different species or the different conditions that start becoming apparent as you dive deeper into the biofilm. So starting from the outside, you've got the 100% oxygen-rich aerobic environment with high ORP. So this point here is the point outside. As we dive deeper into the biofilm, you see you get your typical oxygen depletion. For anybody who's done attached growth system, you know, as you dive deeper into the biofilm, your oxygen gets depleted. And then you get a life boost of oxygen coming with the water. So the actual feed manifold and the hydrous walls are like surface aerators. So they also put oxygen, and hence you get this aerobic boost. And then as you go into the liquid side, you go down, and eventually you cross into the negative and you have your anaerobic regions and you go up. Now, do not be fooled by attached growth. They look simple to the human eye, but they are extremely complex. So this behavior here is on the top of the gills in contact, the closest to the hydrous well. Now, the bottom of the gills, obviously, more anaerobic regions on the inside, and then you lose the oxygen that you supplied with the hydrous well. And I guess the message that I want to get across is different species are able to grow on the BioGill, and things like simultaneous nitrification and denitrification. We've observed that in some of our installation. I'll go to the next slide. That's probably a little bit more on the academic side. This here is like a mass balance, and I'm sort of talking with a few universities and few commercial modelling software, like the likes of BioGill, to try to get it modelled and give basically our engineers and our customers a tool to try to figure out what is the best operating conditions in terms of feed and temperature and the likes to optimize this effect of growing different types of bacteria. So I guess the key message to get from this, without diving into all this, nice to look at academics, is the electron source or the electron donor and the electron receiver, or the carbon source, the food and the oxygen are opposite side of the membranes. And on the inside, we're able, through design and operation, to get anoxic regions. I'll go to the next page. So we go out, and we make the claim that we are an unlimited supply of oxygen, and the sales guys go and say, look, we can do this, and we can treat with no blowers. Why is that the case? So the best way to explain that is if you look at a conventional wastewater fine bubble diffusers, getting the oxygen to the biomass or to the bacteria requires going through what we call 5 steps. So first you got to create the bubble, you got to push it into the water, then you've got to overcome the gas liquid interface, go through the boundary layer, and then once you're in the bulk liquid, you got to keep that mixed. Keep it well mixed, so increase the probability of contact between the gas and the biomass. And then once you get in contact or get closer to the biomass flock, there's another boundary layer you got to overcome, and then you get eventually the oxygen molecule find its way to the with our biomass. Just gonna take a sip of water. So what we've done with BioGill is we simply took this and just hang it in air, effectively eliminating steps 1, 2, and 3. And the boundary layer, or the transfer from gas to liquid, that's where the bulk of the resistance to mass transfer happens. So by putting it in air, we are able to literally have an unlimited supply of oxygen. Now, the things to add to that is, in real life, you'd know that the air bubble is not static like this, it's also rising. So the biomass, not only that you're going to go through all these 5 steps, you only have the time that it takes from when it comes out of the fine bubble diffusers at the bottom of the tank to goes to the top surface level. And after that, you just lose it. And I don't know, last time I checked, probably last year, it was about 7, for fine bubble diffusers, it was 7% transfer efficiency per meter of water. And basically that's because these bubbles rise. While with our system, we don't care about that. It's a static, and the biomass doesn't worry about catching or chasing a rising bubble. Okay, so how we integrate these. So we basically can operate a BioGill as a batch or as continuous. When I say a batch, it's not the actual BioGill, it's the overall configuration of the plant. So as a batch, similar to an SBR, you've got a balance tank, you feed the treatment tank, and then you've got a recirculation pump. And we recirculate the flow over the gills a number of times, proportional to the strength of the wastewater. So the stronger it is, the more you need to recycle, and hence the longer the batch time. And at the end, we discharge. So the advantage of a batch process is, as you might know, especially in the industrial sector, the actual concentration and the strength of their of BOD is not constant. We all, as engineers, we all love to design to a certain set parameter, and we say, look, what is it? What's your maximum? What do you want us to design to? And we design to that, and that's where we give the process guarantee. However, in reality, it's never like that. So a lot of these guys in the breweries, food and beverage, they go through busy periods, high order periods, and what that means, it translates to high strength wastewater coming to their wastewater treatment plant. So for a batch process, assuming that they've got enough capacity in the treatment tank, at the end of the treatment, the operator can take a sample and do a COD. If it's not low, or if it's not close to what it should be, they simply extend the batch time. So they've got that flexibility in dealing with extra loads. Of course, you've got some complexity associated with the batch process, things starting and stopping and fill and decant. Okay, so this is a typical batch treatment configuration. The installation here, we've got the big balance tank, so it's about 2 days hydraulic retention time. And for these guys are quite small but high strength, so they do about 20 meters cube a day. Apologies about the conversion to gallons, and I'll let you do the math. So 20 meters cube a day. So it comes in a big balance tank. They do the pH correction, any nutrient, nitrogen and phosphorus supplement as required. And at the end, it gets transferred into an in-ground tank. This is the in-ground tank. We've got recirculation pumps. They feed it into the BioGill. Now, in this particular case, we put the BioGill inside a thermally insulated room. This is basically a cool room, similar to a cool room you'd see in a restaurant. And the reason we've done this is this customer here is on top of a mountain. It gets quite cold, and we wanted to keep the heat that's generated from the breakdown of the BOD or the sugar inside to improve the performance. And later on, obviously, as they've grown in size and orders, this strength here, we've designed this for 2,500 BOD. They're now feeding it close to 4,500 BOD. So the strength almost doubled, so they've added solar heating on top just to do with what they've got. I've got this customer here. So this customer is a winery in a suburban type factory where they really don't have the luxury of in-ground tanks. So they can't go up and dig up at the ground and put an in-ground tank. So what they've done is everything is above ground. So you've got the balance tank above ground, the treatment tank is above ground, but what they've done is they've dug up a little sump. It's about 1 meter cube from memory, and basically feed the gills, the gravity drain with no restriction to a little sump, and then that two pumps it back, we lift it to the treatment tank, and it goes around. So it's another example where I suppose we can't do in-ground tanks. The other way we can do is a continuous operation. Now, the continuous operation are simpler to the point you can almost literally do it without a PLC, assuming, of course, you don't want to do fancy pH or nutrient dosing. But the actual BioGill component itself is very, very simple. Basically, if there is water in the tank, you've got a pump with an integrated level switch. The pump runs. It doesn't care why it runs. There's water, it runs. And that means that you can get an off-the-shelf pump, literally, and that's a BioGill component. That's all you need to do. And the thing to know with a continuous process, just like a normal conventional process, is you are relying on the dilution effect. What does that mean? It means is, let's say I've got 100 milligram per litre BOD coming in, and the recirculation flow is 10 times as much, technically 9 times, but let's say 10 times as much. That means the actual, as it goes in, it will hit the recirculation flow and then gets diluted. So 100 divided by 10 is just 10, and it comes out at 10. So the bigger this recirculation flow, the more the dilution effect. But obviously, if we want to achieve, if the incoming concentration is very high, or you want to achieve very low effluent, it's probably continuous is not the right one to go. But for industrial roughening, it's just it's a good way of installing BioGill for decentralized application. Another thing I've shown here is I've shown a clarifier is you would need to deal with the solids that come out. And these solids dependent obviously on the strength of the wastewater. We normally work around a yield of 0.3 kilogram VSS, volatile suspended solid, per 1 kilogram BOD removed. So this here is from a dairy farmer in Australia. Those guys do have a sense of humour. You can see they love what they do. I always personally get worried when I deal with farmers with sense of humour, because the more high up they go, the extreme low they get to. So if they get pissed and they get upset, they get upset. They don't muck around, those guys. So when I go and see a customer with a happy sense of humour like this, he goes, okay, I've got to get my act together, otherwise I'll probably end up in the tank. They don't muck around here, those farmers in Australia, I'll tell you that. So what we've done here, this is a dairy. And in this, we've done a two-stage continuous in series. So I've got a balance tank going to a first stage, stage 1. It's got a 1 dedicated BioGill. These tanks are always full. So from the balance tank, the level obviously goes up and down to attenuate the flow, and I've got a pump that's set up to have a constant stream feeding this first stage full tank that's continuously overflowing to the second stage full tank, and that's continuously overflowing to a ton dish here to the sewer. So with this particular example, you'd notice that the treatment tanks are actually quite large, and that's done deliberate. So this is a dairy wastewater, as many of you would know or might not know. Dairy, just get a sip of water him up. Not used to talking too much, but giving it a go. Dairy, the actual sugar in dairy, lactose, is deliberately not designed for bacteria. It's actually a mammal food. So it's meant to be very hard to biodegrade. If it was easily biodegradable, none of us would be alive today, because when we were all little and sucking on our mum's milk, the bacteria in your guts would have ate it all before you even had a chance to absorb it. And that's the easy way of looking at it. The hard way is it's got what we call a very high Ks value, and it's basically the hydraulic retention time required to break it is quite large. So what we've done here is we've deliberately allowed for about a 1-day hydraulic retention time in both tanks, and the idea is any enzymes that's secreted by the biomass or any additional biomass is actually grown into this tank. So obviously we've got a washout rate of 1 day, so anything that grows slower than 1 day will be washed away. However, with that, we've kept a significant activity into this tank, and it's mainly the enzymes that break the lactose into a more biodegradable form. So these units are achieving exceptionally good results, to the point I'm sometimes too worried about quoting it, but they achieving up to 150 gram per square meter per day. So it's 10 times as what we normally publish. Now, obviously, the customer here is not looking at reuse, and they don't want to drink the water coming out. They're looking at sewer discharge, and just by simple things like that, we're able to tackle wastewaters that extremely difficult. Okay, going to the next page, sizing. So there's two ways of sizing this. There's a simple way, which is the flux removal rate. This is typical to all attached growth systems. So, you look at your starting BOD concentration, and the higher it is, the more biokinetic activities, or the faster the reaction. So you go up the graph, and then you go to the left, you work out a gram per square per meter per day, and you work out the total area required. You divide that by 230, which is the number of square meters in our BioGill, and you work out the number of units. So this here is perfect, good enough for budgetary quotes. Customers talking to you, and you don't know if they're serious or not, if they're time wasters. Just grab this, do a costing, work out the units, and just throw that at them. If they want further information, we can obviously go to the next one. So before I say that, what we've done, that simple sizing tool, we took that and we've got a spreadsheet which basically allows you to size or calculate the number of gills without having to do the calcs. But it's all very simple. It's all linear type calculations, nothing too fancy. If we do want to, I suppose, and the reason we do this is sometimes customers ask that. They ask you, what does this do? What happens? Can I do this? Or sometimes you might be looking at a job where the only way to sell it is to they've got no footprint. It's in a city. It's a very tight space, and then questions come up. What happens if I increase the temperature? Would that reduce the number of gills? Or what happens if I increase this recirculation flow rate? How does it affect it? So we use the modified Wills equation. So it's a literature used, approved equation for attached growth systems. Now, the key message to take from this is this equation is not intuitive. You can't look at it and find out, okay, this is what's going to happen if I increase the temperature or if I increase the circulation rate. So basically, it's got all these parameters, nice parameters. So you've got a temperature term here. It's got an area term here. It's got a recirculation flow, what happens. And then it's got this K20, which is dependent on the wastewater. So for sewage, it will have a certain empirical value. For dairy, it'll have one. So you need to plug all these values and find out what is the expected output and take it from there. And the idea is, I guess, the message that I want to get across, and I get that from many people, says, Keel, if I double the recirculation flow rate, does that half the number of gills? Well, the answer is I don't know, because the equation, as you can see, is not a linear one and it's not an intuitive. So you get to basically put this in a spreadsheet and plug it in and find out how these various parameters. And we can certainly obviously work with you to. So if you are stuck or you're looking at an installation, the biggest challenge is sometimes for attached growth on a larger flow rate is the footprint. So if you want to the customers has got the funds, they've got the interest in technology, but the only footprint available is XY, and we need to reduce the number of units. Then we go into things like that. Okay, so comparing BioGill to other technologies. Look, this is, I suppose, unless you've got an actual project, say, then any comparison you do will always be open for challenge. Okay, but what I've done here is just based on our observations and what we've seen in the field. I took a hypothetical case where, let's say, a flow of 100 meters cube a day, so quite small, and a concentration of 3,000 BOD. And I've listed the most popular treatment options out in the market and the BioGill, and I went through a few parameters. So operating hours. So basically, I've got, again, before I step into that, I've got BioGill, MBBR, MBR, CAS, conventional activated sludge, and anaerobic systems. So BioGill, operating hours, low for MBR, and MBR and conventional activated sludge anaerobic are high. MBR, you're going to be involved in backwashers and CIPs. That's time. Conventional activated sludge, the operator constantly needs to monitor the sludge age, maintain the DO control. Anaerobic, you got to make sure that you don't lose your biomass. You might not be literally not be seen as doing much, but you need to be there, constantly watching it. Anaerobic, especially for the high strength stuff, it's good. It's probably, you'd find that as you go and start bidding for jobs, this will be the technology you're up against. So the problem with it is the bugs are very, very slow growing. So you're talking 40 days plus. What that means, if something goes wrong, an unbalanced CIP, power failure, things that actually happen, if the operator doesn't respond quickly and you lose your anaerobic bugs, you got to wait 40 days before they start performing the way they were performing again. And that's quite a long time, which means you need to have someone sitting there watching it. Maintainer hours, similar. BioGill, I suppose, dumb, flat sheet, no moving part membrane, as opposed to, again, MBR and anaerobic, where you've got complex systems. For BioGill, the operator and maintainer have probably one role, and basically we just got to make sure there's no blockages or chokes. Keep the hydrosoil clean, keep the membranes clean. Basically, the walls are removable. You don't need any tools to remove it. They're quite light. It's a one-man job. You take the wall out, you hit it with the hose, wash the excessive antibiomass or opportunistic biomass that's growing on places that it's not supposed to be growing at, hit it with the hose, and should be right. Power consumption with BioGill, again, all we need to do is do the static lift of the water about 2 meters on top of the gills multiple times. So if we're doing this 5 times, that's 10 meter lift, or doing it 10 times, it's the equivalent of 20 meters lift. So that's about 2.2 meters plus half a meter for the hydroswirl, so 2.5 meters is the pressure loss you've got to overcome to feed the BioGills. The low for MBBR or anything that's use fine aeration. Obviously, due to inefficiency of the fine aeration, you need a lot of power. Anaerobic, obviously very low power consumption. You could even argue that it's negative, it generates power, but be wary, because when you start dealing with gas, the complexity adds up. You need equipment that's spark-free, doesn't generate any sparks, or intrinsically safe. The gas needs to be of good quality. I mean, remember, these are biological gases. If it's got any inerts or crap in it, you need to filter that. So dealing with that is not easy, and the actual capital cost required for gas handling equipment is very significant. So literally for small jobs, and we certainly found out anything less than 300 meters cube, the customers just don't go with anaerobic because the payback is too long. Operation chemicals. So these operation chemicals are the ones associated with the technology itself, not the process. So BioGill as a technology, we need no specific chemicals. We don't need anything. Same as MBBR. Now in MBR, they need chemicals to batch their CIP. Sometimes they do an acid or a caustic CIP. They need chlorine. They put that into the backwash. So their technology, these chemicals are with the technology. Conventional activated sludge, you don't need any chemicals. Now anaerobic, the reason I put yes here is for chemicals is the actual biology itself, the anaerobic biology, as some of you might know. It's quite complex, and it's a consortium of many different bugs working together. So the very, 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 very simple way of putting it, you've got the acid forming and the methane forming. So what the operator needs to do is to make sure that the acid formings do not overgrow their space. So they're constantly watching the pH of the anaerobic digester or anaerobic reactor, and they need to do that because the acid formings deliberately want to actually kill everybody else to keep the place for themselves. They want to drive the pH down, and if that happens, it's a term we call souring of the anaerobic digester. And what the operator needs to do is they need to keep an eye on that, and they need to either lime the digester or add caustic. So that's the operating chemicals. Cleaning chemicals, not required, MBR required, not required. That's mainly the CIP. Resistance to high-load fat, oil, and grease. So because of the biomass, or the bulk of the biomass, or the critical biomass is growing on the air side, there's an actual physical barrier between the biomass and the wastewater. So if you do have a high load fat, oil, and grease, or if someone does dump in big drum of oil into the wastewater, the actual biomass flock will never get covered, will never get suffocated. As opposed to an anaerobic or MBR or conventional, if the flock is smothered or covered with the oil and fat, oil and grease, it gets starved. And it's a matter of time. If it can break down the fat, oil and grease quick enough, it might survive. But the likelihood, especially anaerobic ones, they're too slow to act. If they covered a little bit of fat, oil, and grease, and you've lost your bioreactor. Now with BioGill, the biomass still has access to oxygen from an opposite side. They still have reserves of carbon source within the biofilm. And what that means is they're faced with a challenge, and they say, look, if we're going to survive, if we're going to access the carbon source, we better do something about this fat, oil, and grease. They start making the enzymes required to break it down, and they tackle the problem, and they're able to deal with it. So we're quite very tolerant. Up to 100 milligram per litre fat, oil, and grease, we've observed our system to operate without an effect on performance. Recovery after a toxic shock. So this is probably related most to the actual biology of growing in a biofilm. So biofilm is the natural way bacteria evolve to grow in nature. They don't grow as a flock swimming in an aerated tank. This doesn't happen in nature. In nature, they grow as a biofilm. It's a full community. And what that means, has many meanings, but how it applies to a toxic shock is two things. When they grow as a biofilm, they're able to keep the weak. When I say the weak, is spores, little babies, species that are just there for storing genetic materials. And basically, because they're in biofilm, these things don't get washed out. So they're there forever. And the biofilm deliberately puts it there as the reboot. It's a safe mode of rebooting. If you do lose everything, these guys are there. We've got all the information we need. We can reboot, and we can never wash them out. The other thing is because of the planar way, you got to remember, a flat sheet biofilm has layers, and it's like an army with lines of soldiers. So if you do have a toxic dump, someone goes and the one we observe the most, especially in sewage, is fuels. Someone goes and dumps in fuels or hydrocarbons or something like that. It's the first layer, or the first flat layer closer to the biofilm, is the one that's going to absorb most of the shock loads, effectively protecting all the other layers further or closer to the air side. It's just the nature these things work. While in a conventional way, we've got little flocks running all over the place. The minute you have a toxic waste dumped into your bioreactor, instantly all the biomass, the bulk of it, is in contact. And hence the kill is massive. While with BioGill, of course you'll get a kill, but after the conditions that caused the kill or you rectified it, the recovery is very fast. So a system, for example, if it's starting from a clean slate, brand new, shiny white membranes, could take 3 to 4 weeks. If it's starting after a toxic kill, it will get there in a matter of days. So the last one is the modular. And when I say modular, is you can add or you can upgrade your plant, or you can respond to extra loads at one BioGill unit at a time. So you'd find that most of the customers grow slowly. Nobody goes doubling their capacity overnight. So you design a plant 100%. Next year they're 110, 120, 130, 140%. So the typical way is people wait till it's 150 or more, and then they just mimic or build a copy of their existing plant side by side. While with BioGill, if you say you've got 10 units and the customer's got an extra 10%, no problems. You keep all the infrastructure the same, you just add another BioGill next to them. And basically you've increased the biomass inventory of your system. And that sort of concludes my part. I'm sure a lot of you have a lot of questions, so what I'll probably do, leave the questions till the end. I'll try to get to them the best of my abilities. Anything that requires calculations or further research, we'll probably get back to the questioner later on.
That's right. Thanks very much for that, Akil. So I'll finish up walking everyone through, I guess, the practical applications of where we currently have commercial projects running and where we see BioGill being most competitive from a technical and a commercial point of view. Thank you again for all of the questions that have come through. As Akil mentioned, we'll address them at the end. We've left a bit of time for this, and we're more than happy to stay on a bit later to cover them. So from a business point of view, we've seen the most success from our commercial projects, of which we have over 220 units running commercially across the world at the moment. And these are primarily within sewage and food and beverage industries. I'll go into the basic specifics of each industry now, and if you'd like any additional information on our specific projects, case studies and technical reports, we do have these available at our website, or you can email me, which will be on the final slide of the presentation. So we've determined what we considered the sweet spots, which again is back to the technical efficiency of the unit, but also the commercial viability of the unit being implemented on a given project, and come up with a number of options which Akil has spoken to previously when comparing technologies. The main clientele, or the end users of the BioGill that we recommend our distributors targeting, are the small to medium-sized food and beverage manufacturers, and this is for a number of reasons. The first, as Akil's touched on previously, is some of the more traditional systems, such as MBR and the anaerobic digesters, can't necessarily be considered financially competitive for flows under around 500 cube a day. And there's also, I guess, a focus from these customers that they want to operate primarily on their core business, which is making beer, making wine, making candy. And the concept of dealing with wastewater is a bit of an afterthought. And in fact, sometimes it's quite a rude awakening for them. As we've seen in Australia, I know it's happening in the US and a number of the other countries in which we're operating. Water utilities and environmental authorities are starting to clamp down at wastewater at the source. And this is due to, I guess, the traditional municipal plants being overburdened, but also the utilities seeing it as a bit of a cash cow that they can charge these producers if they're discharging, I guess, higher strength wastewater to the sewers. What we try and focus on ideally, and we've won a number of awards with some pretty big companies, Ferrero, for example, in Australia, we've dealt with a lot of very high strength food and beverage wastewater, is we're very, very effective at tackling high strength BOD around the 3,000 mark. However, the dairy that Akil mentioned previously, that was the continuous flow, I believe, was designed around 4,000 and it's coming in at 60,000 BOD at the moment. What we're really looking for are the clients that are facing these discharge fees due to increased regulation, and also clients that are specifically looking to have more of a sustainability outlook. It might be a corporate social responsibility goal driven by the corporate body of the existing plant, but it's primarily in the food and beverage manufacturers that are focusing on candy or confectionery, wineries and breweries. And this is simply due to the biomass that we grow for these types of applications. Another really pertinent area to consider is clients that are concerned with high electrical costs. For instance, some of the areas we operate in Southeast Asia, electricity is extremely costly, and this is actually, I guess, reducing profits significantly. When you can talk to these clients, and I guess money makes the world go round, and you can tell them not only are you not going to be stung with discharge fees, but your electrical costs are likely to be reduced, you see some pretty big smiles spreading across their face. And the last point I'd like to touch on for food and beverage, which will also flow into the sewage treatment, is retrofit as a performance boost. As Akil mentioned, the technology is designed to be scalable and modular, which allows us to be retrofitted over an existing system, which might be aging and no longer working to full efficiency, or also if these clients are looking to increase their production. So traditionally, the only other way you could increase the performance is to go and build an exact plant next to it, or some operators might just increase the aeration, get a few good days of treatment, then unfortunately wash out all of their good bacteria and be back to square one. With a BioGill, you can retrofit it over the top of an existing system, and the capital costs and actual labour required for this is very minimal. Which brings us to our second sweet spot, which is sewage treatment plants. So this can be seen as a standalone system for a smaller resort or decentralised restaurant, golf course. We currently have putting in Sydney, and we've got a number of installations on some remote islands in the Pacific as well. However, we're also seeing quite a bit of demand, as you can see in the picture here, for sewage treatment plant upgrades. So this is the municipalities that were built 20, 30, 50 years ago, and the population surrounding the area has increased whilst the plant's performance has remained the same. So they can either be hydraulically or organically overloaded, and again, the only real option is to build another plant right next to it. Alternatively, the BioGill solution allows for a retrofit to be placed on top of the plant, as you can see here. And this can be either as a parallel stream or just taking on the brunt of the force and supporting the existing plant. A few of the more generalized sales propositions and benefits that we have from BioGill, Akil's touched on the majority of them, but just a bit of a background from, I guess, where John and our original shareholders came from with the technology is simple is good because simple doesn't break. And as I mentioned before, we're in, I believe, over 18 countries around the world now, and they're very, very different. The US to Australia, to the backstreets of Thailand, to parts of India and South America. Obviously, the desires and the capabilities of these operators and clients changes. In some places, there's a saying that if it breaks, it stays broken, and to rely on regular and highly intensive maintenance is to your own detriment. So we've designed these systems to be simple to install from our distributor's point of view, but also really easy to maintain. I guess another one of the key benefits here, in addition to the ones that Akil has already touched on, is we do have a number of projects that are commercially running purely to treat odour in meat processing and dairies, as well as sewage treatment on resorts. And this is, I guess, a pretty intangible cost that it's hard to put an exact price on. But if you're running a winery or a dairy and you're having guests and tourists arriving, a bad odour can really cost you business, and it's a lot harder to put a financial amount on. And the last one I'd really like to touch on is the fat, oils and grease treatment, which Akil was talking about before. We're actually the only biological system approved by Sydney Water, which is Australia's largest water utility, to treat commercial kitchen grease traps. So Sydney Water did some quite rigorous testing and determined that because of the design and the two patents that we have, which is the nanoceramic gel and the looped membrane with the liquid gas interface, our biological system is able to handle these high levels of fats, oils and grease without being suffocated. We're going to move into the questions and answers, but just before we do, for those of you that have to run, as I know it's 5 o'clock on the East Coast, I believe, just a quick little direction for you. If you have any questions about today's presentation, you want the slides specifically or case studies and technical reports relating to particular projects that we've done, please feel free to send me an email. We also have the majority of our case studies available on the website. For ongoing news and updates, if you could follow us on our LinkedIn, which is simply BioGill, or the link is here. You'll also get more releases in terms of what we're doing around the world in different markets. Every time we find a bit of new data or performance results, we post them on there as well. And you'll be able to get updates on the next webinar, which we're running again on the 27th at the same time. This is something we're looking to do more so moving forward as we expand into the US and some of the other key markets we're looking at. And we'll be running webinars on different applications and theoretical designs maybe for a specific industry. So I know that we had a lot of questions come through, and as Akil mentioned, we'll do our best to go through them. We're more than happy to stay online a bit later, but again, if you do have to leave, thank you very much for your time. And apologies if these questions aren't necessarily in the order they came through. I'll throw them out to John and Akil, who you can see their lovely faces. I'm not allowed to have a photo up there because I'm not photogenic enough. But let's get down to the questions. So perhaps the first one that's come through, Akil or John. What is the max loading rate on a volumetric basis? So what can one unit treat in terms of kilo per POD per day, or is it designed on the square metre of the gills themselves?
It's basically, I guess, we work in gram per square per metre per day, but it won't be hard to actually answer this question. So for typical sewage, when I say typical domestic sewage, 300 milligram per litre BOD, one unit can do up to 10 metres cubed per day. This volume goes up as the concentration of the BOD goes down.
Okay. Back to maintenance. What needs to be cleaned, how often, and how do you remove the excess biomass from the system? Can you use a pressure washer on the gills?
Yes. So basically, excessive biomass, it's a mechanical detachment. Whichever way it mechanically detaches, you can even use a combined water compressed air, shake the gills, whichever way to basically BioGill that's growing on top, BioGill that's growing on the sides, hit it with a hose, and yeah.
Do we manufacture the ceramic membrane, or is that done by others?
No, we manufacture the ceramic membrane here in Sydney. The plastics that we now have an assembly hub in China. So the plastics are coming from China, which are the other main components in the system. But we have control of the ceramic membrane here in Sydney for a couple of reasons. One surrounds the IP protection, and the other one it surrounds the ISO 9000 accreditation. So we're making sure that the quality is up to scratch.
What is the typical length for a municipal batch, and how much can one tower treat? Which I guess you touched on before, but Akil, maybe it'd be worthwhile talking about the Middle East project where they tested.
So for low strength, when I say low strength, this is quite variable. So we could go up to 4 hours to get the BOD down, starting from 150 milligram per litre BOD. As it goes up, the hours need to go up.
Okay, what is your patent position versus Oxymem, Dow, GE, etc.?
Okay, this is mainly for North America. Oxymem and GE have got a product they now call MABR, similar to the MFC system, which came out of Israel. All of those patents, from what I can gather, are fairly new. Oxymem around 2008, MFC around 2011, and GE launched their Xelon product at WEFTEC in 2015. The BioGill patents go back to 2005 and 2006 when they were first taken out by the Australian government through ANSTO. And we've since added to that. So we took the original patents, we've since added with the new BioGill tower and the HydroSwirl dispersal system with applications this year. So the BioGill patents were enforced, from what I can gather, before any of those other ones come to play. But also it's a very different process. All of those MABR systems tend to be submerged, so they tend to be a drop-in type of plate with a hollow core membrane which is dropped into sewage treatment systems. Ours is above ground, so it's quite a different application.
Okay, so decreased or inconsistent treatment due to sloughing is common criticism of trickling filters. How does BioGill relate to or address this issue?
Yes, that's a good question. So it all comes to the design. So by keeping the load on the BioGill within a predetermined design parameter, you actually select for the right biomass that can self-optimize. So what we've seen is, if you keep the biomass aerobic, it looks after itself, and you don't actually get faced with these challenges. If your load goes up and you're getting issues like that, then the question is might be an opportunity to increase the capacity of your plant.
So there's a few more questions around the particular design and management of sludge. How do we move sludge to a clarifier, and must we use a mechanical clarifier, or can a hopper clarifier be used, or another type of separator?
Again, this is dependent on the application. So for sewage, for example, you don't need a clarifier. The actual BioGills themselves, they've got a filtering capacity, and the effluent that comes out of them can be fed directly to a filter. So what we found is typical solids coming out of the gills are about 30 milligram per litre. As the strength goes up, the sludge or the biomass that comes out of the gill is not like a conventional wastewater sludge where it settles like a clarifier as a blanket. You can use a DAF or a hydrocyclone. So it's something to do with on a case-by-case basis.
Okay. Would you say that continuous flow tends to be more cost-effective, but batch flow is needed for specific or unique treatment needs?
Yes, definitely. Continuous is cost-effective and easier, but batch has more flexibility and able to meet higher strength quite easier than a continuous.
John, maybe you can talk through some of our systems and how long they've been running commercially.
Yeah, the original ones that we installed from a commercial basis were put into the Fiji Islands in 2011, and also here in Sydney in a tourist park. So they're the longest running ones we have. They've been running for about 5 years, and since then we've had a rollout right the way across. The government had done a number of installations prior to us coming along, but they were mainly in the demonstration phase. They weren't commercial.
Okay, so I guess just to clarify on that, our longest commercial systems have been in the field for 5 to 6 years, and obviously increasing project rollouts from there. Akil, what is the peak influent BOD feeder system, and does it clog with higher organic levels?
Look, I suppose what we recommend is up to 3,000 BOD, which is where I've got good solid data. Having said that, there are customers out there that are feeding a lot more, but at this stage, we sort of like to stay around the 3,000 BOD.
Okay. Could one suggest that the gel used decreases sloughing and or increases the recovery time?
It certainly increases the retention time. The gel that we use is a very good housing for the microbes to grow and flourish. We have a longer growth cycle on our microbes because of the oxygen availability. So we can have microbes that form into a biomass and will live inside the system for sometimes months, compared to most other systems where they don't have such a long lifespan. And the gel that we use becomes that perfect housing. So the microbes will grow and they'll get thicker and thicker depending on the strength of the nutrient. Once they get to be quite large and thick, then they're oxygen depleted. So oxygen can only penetrate for 1 or 1.2 millimeter, and then you find that the biomass will start to slough off automatically.
Conventional trickling filters that are subjected to high loading are often oxygen limited at the top of the filter, thereby decreasing overall effectiveness. Can you speak to the similarities and or differences with regard to BioGill?
Look, we sadly don't like to be compared to a trickling filter. A lot of people compare us to a trickling filter, but we are not a trickling filter. It looks similar, but we are not. In a trickling filter, the carbon source of the and the oxygen are fed from the same side, while with BioGill, the opposite. So that's a very key difference, and hence you'll never get oxygen limited or starved.
Okay. There's a question come through on fats, oils, and grease, Akil. Is our maximum limit for FOGs 100 milligrams a litre, or is that what we recommend?
It's what we recommend.
Okay.
Yeah. Well, I can tell you that we've completed projects in Southeast Asia with far greater levels of fat, oil, and grease, up into the hundreds. I think that in some of the fast food chains that we've had systems installed in, we've gone up to as high as 1,500. And we've had a very good 90% reduction in those applications. We're recommending 100 as a safety option, but we've been in much higher environments than that.
Oh, you guys are eating up the questions. Okay, I'm just going to try and keep pace here, so apologies if we take a little while to get to them. With treating odour, is it by treating liquid stream or the gas stream?
Yes, this is not a gas treatment system. It's actually the high volatile organics in the liquid stream. So it's liquid, not gas.
Is the startup time required pretty constant, 2 to 3 weeks, regardless of the type of waste? So perhaps here we can talk about both of our sweet spots as well as potential seeding.
No, it's not consistent. In sewage treatment, it tends to be very fast, and we've seen a solid biofilm grow in the gills within 24 hours. In some of the food and beverage applications, it can take up to 6 weeks, and that's because some of the microbes are slower growing. When you get to the more the higher concentrated organics, we find that the microbes that deal best with that type of influent are the slower growing ones, whereas sewage is quite quickly. So it tends to be inconsistent depending on what we're dealing with.
So just to add to what John said, so BOD or heterotrophic type bacteria are very fast growing. So if it's only BOD, you don't need a couple of weeks. I guess I quoted that for nitrifiers. So nitrifiers are very slow growing, or if we're looking at nitrogen removal, obviously we got to wait for them. So they're much, much more slower, and basically it's the biology, and you got to wait for them to grow.
Great. Does the biomass grow on both sides, the air and liquid, and which one is shown in the previous pictures? So I'm going to go back to the original slide, and Akil can talk through them. So Akil, to clarify, this biomass here?
Air side?
Air side?
Yep.
And this biomass here?
Liquids.
Okay, and the difference between the two?
One is aerobic, one is anaerobic.
Okay, great.
And the answer is yes, it grows on both sides.
Okay. What other questions?
And you got to remember that's a key difference to the membrane aerated bioreactors. So, there was a previous question about all the oxymem and MFC, and we very, very different to those guys. So they basically got an air side that's hydrophilic, and they deliberately don't want water or any biomass growing, only the oxygen, while we actually use all that room to grow biomass and provide more bacteria.
Another question on operation and maintenance. The pictures indicate that plugging could potentially be an issue. I'm not sure if this is in reference to the outlet or to the top of the gills, but Akil, can you speak through to both of those?
What's plugging?
That would be that we're getting so much biological growth that actually starts to block the system.
Okay, so basically, yes, obviously, this for some of the earlier type feed manifold, we actually had a simple gravity pipe manifold with holes, and we absolutely right, it clog up and fill with biomass. So what we've done, I guess, evolving and responding to that is with the hydroswirls, there's a little channel in there in the hydroswirl that has a very, very high velocity. So it does two things. Because of the high velocity in it, the bacteria doesn't grow and it constantly washes itself. Now, the membranes themselves, we've fed them with some of the retrofits. We put these BioGill on top of an existing SBR with 3,500 milligram per litre MLSS, and they didn't clog and it didn't matter. As a matter of fact, it actually improved the system because it was providing a constant seed source to the BioGill, and it was constantly challenging the bugs on the gills to make sure that we selecting for the better working and more efficient ones.
Right. Can modifications be made to the look of the BioGill technology? So, John, perhaps you could talk about what they've done on Manta Ray at Symbio and what we did for Ferrero.
Yeah, as far as modifications are concerned, yes, the system is quite that lends itself to doing that sort of thing. There's some aesthetics that we can do. For example, for some distributors, if the volumes are there, we can brand the product as a private label if required. But as far as the look of the system is concerned, on a larger project whereabouts we're putting a number of them together, we would tend to assemble those inside a treatment room itself, and that can be put in any configuration to suit the application whereabouts we're being installed. In Manta Ray Island, they've actually coloured the outside of the reactors to be in more of a garden green, so it would be aesthetically pleasing. They've simply spray painted that themselves. And in a place like a zoo such as Symbio, they've put a black cloth over the outside of the bioreactors just because it suits the environment better.
And just to add to what John said is we can actually sell the unhoused unit or the cartridge. So similar, if you've dealt with the likes of a desalination membrane, you've got the actual membrane is one product and the housing is actually a totally different product. We're more than happy supplying the actual unhoused or the filter itself, and you can put it in whichever housing you'd like to put it in, and we'll work with you to make sure that any process needs that needs to be addressed are addressed. No problems there.
Right. So I'm hoping that we've addressed all the questions that have come through. If we've missed anything, we can hang on for a few more minutes just to have any final questions sent through. Alternatively, if you think of something that we might have missed or you need a bit of time to digest all of the information, again, please feel free to get in contact with us. We're very excited about the next 6 to 12 months at BioGill as we continue our expansion into the US, and we have a number of commercial projects on quite a large scale that are being finalised within the next couple of weeks to couple months as well from our end. So again, please follow us on our LinkedIn for more updates in terms of the projects that we're putting in. There'll be a lot more technical reports and case studies coming out of this. And just a friendly reminder, we're also doing the same webinar again on the 27th at the same time. So if you have any potential clients, business partners or colleagues that you think would enjoy this one, we'll be running the same thing again. So thank you again, and very, very appreciative for all of your time. And we look forward to hearing from you all soon.
Thanks all very much.
Thank you, guys. I look forward to working with you.